So how this recurrent neural network works. So here you can see we have some data, yeah, which is hot encoded. So here we have some text, yeah, and that is converted into some integers, yeah, and then now we can fit this data into our recurrent neural network. But actually, how this recurrent neural network can analyze data, yeah, text data. So here, as you can see, we represented these features in with some binary numbers, yeah, and then as you can see, we provide this data, yeah, in a sequence with some neural network sequentially. So here we have feedback loop, yeah. We have like Wi is a input weights, yeah. We multiply with some input weight. We also take output from some other neural network which is connected sequentially, yeah. So when this neural network works, it's not considers only input data, yeah, as just fully connected layer neural networks, but it also considers input output of the previous, like next standing neural network, recurrent neural network. So it considers like input, current input, also output of the some other recurrent neural network. So as you can see, it has so here you can see it you have connection within each neural network, but it also has it also considers information from its own output. Main difference of a recurrent neural network from fully connected or feed-forward neural network. This is a graphical representation, yeah, of recurrent neural network. And here, recurrent neural network has different. It can be created in different way. For example, here 1-to-1, yeah. So it can be just to recognize, to capture time series data, and here one-to-many. This can be used, for example, you provide some image, and it will describe this image, yeah. It can generate some text. So in such case, this is called one-to-many relationship. Here, for example, segment classification, you're providing some several information in time series, and it outputs only one result. Here, for example, in machine translation, you provide, for example, a sequence of texts, yeah. So it means you're providing some amount of information, and at the output you have also another amount of that. So this kind of many-to-many relationship is used in machine translation. Here it also can be used to video classification, yeah. So here, yeah, where it can be used one-to-many relationship, yeah, music generation, image captioning, and so on. So here, many-to-many relationship, many-to-one, yeah. So it you provide some time series of data, and it can provide like at the output like positive, negative, or neutral, yeah. It's in sentiment analysis. Or you provide some email text, and it at the end it says like, is it spam or not spam, yeah. So one result. Here example of many-to-many implementation, yeah. So as we previously mentioned in machine language language translation and so on. So this is what we told before. So many-to-many architecture actually is also and the difference from others. It consists from encoder and the decoder part. So encoder part is, as in computer vision algorithm example, yeah, as you see, you compress this information into some low dimensional space, which has the most key information, yeah. But the decoder part will from this lower compressed information data, it again expands this information into another type, yeah. So this is how, for example, given like English language, it will translate to French language, yeah. So here we also have backpropagation, yeah, in recurrent neural network. So you have multiplication with some output of the previous neural network and the bias, yeah. We also imagine we providing some text and it produces some output, yeah. But we also have true correct text, yeah. And here we calculate loss function. So here, as you can see, yi actual grand truth value and the y y with hat, yeah, predicted value by model. So here we also, as you can see, we also update weights, yeah. During backpropagation process, we have different weights, yeah. Input weights like hidden state, yeah, with self loop, and the output weights, yeah. So all of these weights is updated, yeah. Here theta is a learning rate, and the L is a loss function, and we take derivative with chain rule regarding to these different weights. So it means if the loss function is big, we update a lot these weights, yeah. And if it's not big, or if our loss function is close to 0, there will be a less update. So here how weight update process happens, yeah. So we updating different weights. Here the chain rule is implemented. So chain rule, it means like we updating weights I, yeah, regarding to the loss function, but we also consider different like we prediction output, yeah, and so on, and the intermediate values of our recurrent neural network. But we also have problems with recurrent neural network. So it has a vanishing gradient problem. So vanishing gradient problem is about, imagine we have long sequence of recurrent neural network and some other fully convoluted layers, yeah. So when we calculate this loss function, here when we calculate loss function and taking derivative, and when we propagate backward to initial layers, our sometimes error becomes close to 0, and then your neural network starts to not to be updated. So then your model does not learn longer. So this causes makes problem with capturing long-term dependency. So in order to solve this problem, LSTM long short-term memory neural network is created. It has much more complex architecture, yeah. Here we so it has like input gates, yeah, and there is also forgot gate and the output gate and the hidden states, yeah. So here you can see there is two activation function exist. So here you can see like from how much information how much processes it has, yeah. So here it has input vector, which is xt, and it has like memory from current block, CTI block, yeah. Also it has even 3 activation functions, yeah, with sigmoid. Also it has element-wise multiplication, also hyperbolic tangent activation function, and here HT is output of the current block, yeah, and it also considers output of the previous recurrent neural network. So as you can see, it has several processing stages. So one of them is a forgot gate, yeah, so which decides which information is necessary to memorize and which information can be forgotten, yeah. So which takes 2 input, yeah, from previous cell, and the other is input of the current cell. So also it has input gate. So it responsible to if it changes its information depending on current information or not, yeah, if it changes internal state or not. And here it has like activation function using tanh, yeah, which can take +1 if it wants to pass this information, or takes -1 if it's not, will be updated. So we talked about input gate, forgot gate, and here output gate. So now we come to output gate. So here this gate is responsible for selecting important information from current cell and show it's as output, yeah. So it uses previous output and the current input, yeah, and regulates which information should be shown as a output. So it can vary from -1 to 1, yeah. So there is 2 activation function used, yeah. So sigmoid function and hyperbolic tangent output. So this is about natural language processing or time series data processing related neural networks, yeah, which is a recurrent neural network, and long short-term neural network or LSTM. But another paradigm is called reinforcement learning. So reinforcement learning algorithms learns from. So if we before was providing some labeled or unlabeled data, yeah, in order to just to understand underlying structure or pattern, or we provided labeled data, yeah, this is a cut, this is a talk, and a train our model. But with reinforcement learning, it's also called sometimes mainly agent, yeah. It learns through this algorithm can act in some environment and learn to do some correct things, yeah. For example, it was first time created with some testing, yeah, with dog. For example, let's say if dog has done some necessary actions, required actions, it was rewarded, yeah, giving some bone. Or if this dog did some bad thing, for example, not required action, it was punished, yeah, it was receiving bad reward. So giving this, doing these things iteratively, we can teach dog to do some unusual things, yeah, for the dog. This is how this algorithm is initially was created. So it has some agent which can do some action, yeah. So based on this action from the environment, it receives some reward, and it also measures his state, yeah, what he's done. And receiving this state and reward, it will do some other action which will increase the reward, yeah, because we all of us need some positive reward, yeah. We don't need for example punishment. So in such way this agent learns to do some necessary actions for us. Here, for example, in game, yeah, for example, we have several actions, yeah, which we can do, which we can define by ourselves, and then we can estimate or observe our state, yeah, and also get some reward. And having this information into our agent, we will learn how to do some correct things. So in reinforcement learning, we have several things which is important. This is a state, action, reward, and the next state information. So here reward, yeah. So reward is a central idea in reinforcement learning. So this agent learns this to act in this environment in order to maximize cumulative reward, yeah, from its action. So here, for example, in chess, yeah, in chess we might provide, for example, some rules, yeah, for example, in which direction each object can move, yeah. For example, we can define rules, and in what case it can receive like positive reward. In, for example, if it's lose its one gamer, it will take negative reward. So in such case, by defining rule and by defining what is a bad and what is a good for playing chess, for example, we can train our agent can learn with trial error, and even it can win some good player, yeah, because it learns also, it memorizes what actions was good and what actions was bad, yeah. So here in, for example, chess, we have this kind of state, yeah, which is fully observable, yeah. We can exactly know where we are staying and how we can move. So it's fully observable state, but there might be case which we cannot observe fully our state, yeah, partially observed environment, it's called. This was for example, Super Mario Bros. Is a partially observable environment. So here we said like about observation, yeah. We can observe our environment, and also action space. It's all possible actions, yeah, that we can do. So we should, in order for our agent, we should define all the possible actions in which we can do in this environment. So we should define what we can observe clearly, and what we can do as an action. So, and what is the rules, yeah, by doing what these actions, yeah, what kind of actions will provide for us good reward. If we define these things, we can train these reinforcement learning models. So here this reinforcement learning actually used a lot in autonomous cars, yeah. In order to do that, they usually train these reinforcement learning models in simulation mostly, because we don't want our expensive cars always be crashed during training process, yeah. So in order to train such models, we should provide much more close to our real world simulation environment. So here the important thing is here how we define reward. Yeah, so because our agent task is to maximize this reward, yeah, cumulative reward. So here in this task, for example, these mice should eat, for example, these cheeses, yeah, while avoiding, for example, cat. So we can, for example, write clear reward system, yeah. For example, if it by moving this in this direction, if it founds, for example, sees cheese, and it has pleasure, yeah, and since it will receive some reward. But for example, if you go, for example, to this where a 3 cheese is located, if you go, it receives more reward, yeah. But once it was captured to the cell or go to the cell of cat, if it was eaten, then it receives very bad reward, yeah. So we should define such a reward system clearly in order to train this model. So here in reinforcement learning reward system, gamma term exists, yeah, which is called discount rate. So this gamma regulates if you consider like future rewards, yeah, or if you consider instant rewards. For example, imagine like eating always one cheese gives you only one reward. So we always want to find easy ways to increase reward, yeah. Or sometimes we might consider different cells and try to some other things, and maybe in some place we can find 3 cheeses, yeah, in one place. So then we increase the reward much more higher. This term is to regulate if you want to increase reward instantly, or we can sometimes miss rewards in order to increase our reward in future, yeah. So actually it's mostly was defined for static discrete systems, yeah, but it was difficult to define for continuous problem. There is, as you see, there is exploration and exploitation trade-off. So imagine you are, for example, a person, and you in some place tasted a good meal, yeah, in one cafe, and instead of exploring some other cafes, you always go to the cafe that you know, which has good meal, yeah. So you always go there, and they don't want to explore some other places. So, but there is might be case where some cafe provides you more good condition, yeah, good meals and so on, good emotions. So that's why it's very important to define for the robot, yeah, the amount of new ways of trying some new things, yeah, in order to explore its environment. Or always, so this is a gamma term, yeah, or it can always try to increase its instant rewards, yeah. It's similar to visiting always to the known places, yeah, without exploring some new places. So there is policy-based method in which you, for example, you directly learn policy, yeah. So what things is good or what things is bad. So you learn like good actions directly. There is also in reinforcement learning value-based methods exist in which you visit some place and you receive some reward, yeah, and these rewards is then written for each state. So it's state related, yeah. Being at this state, is it good or bad? So there is some numerical representation as a reward, and then your task is to maximize these values, yeah. So here it's a way of value-based methods. So before, deep reinforcement learning was like implemented with Q-table. So Q-table is shows like this. Will be state and the actions here. For actions, for having some actions, what kind of state was observed, and what it was a cumulative reward value. Yeah. So it was like you have, for example, in chess. Yeah, we can write each state. Yeah, for example, what kind of state was where is some players was staying, and some actions. Yeah, we record this information, and each after having filling this all of this information, you can easily find good actions. Yeah, because you know what was the action in this case, in this state, what kind of action you have done, and what was the reward. Yeah, cumulative reward. Now having all of these combinations, you might just select being at this state, you might just select these actions which was providing good reward. Yeah. So but for small dimensional problem, you can easily implement this kind of Q-table. But having continuous, yeah, for example, in driving car, you have different angles. Yeah. Or also in, for example, what you're observing, you have different states. Yeah, you might drive on snowish road, or in the street, or in the outdoor. Yeah, out of the city, for example, roads. So as you can see, you also have brakes and the gas. So all of these states, if we take into account different combinations, our possible actions will be increased a lot. So that's why in high dimensional problems, this Q-table is not applicable. So that's why neural network based reinforcement learning is created, which can be implemented for continuous state problems. To find optimal policies, you can use policy-based method, yeah, and value-based methods. So this is like general overview of deep reinforcement learning, and we didn't stop into details, but there is like Bellman equations, also Markov decision process is involved, and but we don't have such time in order to observe all of these techniques in detail. Yeah. So here key points in reinforcement learning. So this is the algorithm that can act and learn from interaction with real world, yeah, with or some artificial world. And in this algorithm, the key point is to maximize reward, yeah, cumulative reward, by doing some random action. So this algorithm learns from its own action. So in order to do that, we should clearly formulate what is the observation space here, what it can observe. For example, for us, it's our visual sensing capability, hearing, and some senses, yeah. And our actions usually can be done with our hand and the legs, yeah. So we have clearly our sensors, yeah, so what we can observe, and our hands, legs, yeah, which can do actions. So we should define clearly what is the action states and the reward system. For example, what kind of for example, observing this environment and doing actions, what was pleasure for me. So next time I want to increase these actions, which provides me more pleasure. Yeah. So this is reward system. Or doing some actions, for example, touching fire. It was for me, for example, bad situation. So next time I will try to avoid touching hot things. Yeah. So this is, we should reward clearly describe what is a reward system for this agent. Yeah. So defining these things, we train our reinforcement learning models, algorithms. So thank you for your attention. We covered like general paradigm in AI. This is a computer vision, computer vision algorithms, and how we can process natural language models, and another paradigm called reinforcement learning, where we do not provide any labels, anything, but it learns from environment through trial and error, which want to increase reward. And we also covered different type of machine learning algorithms, simple machine learning algorithms, and different problems like regression or classification and so on. So thank you. It was a pleasure to you provide this kind of lecture. I hope it was very helpful to you. Thank you for your attention.